Thank you very much. So actually, Sania Fiedler, who's sitting over there, and I were supposed to share this section, and we decided that instead of, bombarding you with many things, only one of us was going to give the talk. So we played this very sophisticated game that you probably have seen before, right? And it turns out that either I lose or I win, depending how you see it. Okay. Can I have a slide? Okay. So my talk is all about videos, so I cross my fingers. Okay. All right. So today I'm going to be talking mainly about imaging in the context of self-driving cars, because I thought that it's a very exciting topic that probably all of you can relate to. And I don't need to convince you that there is a lot of economic value in this. We've seen with Lear, right, that in 6 months you can generate a lot of $1 million. There is also a lot of value for our society, and in particular I'm excited about public transportation. So if we look at systems these days, right, they're pretty good at driving in highways, right? The trucks are one example. And so if you think about it, these systems are pretty good at doing things like localization, path planning, and obstacle avoidance. And in order to do this, typically they rely on sensors that are actually quite expensive. For example, the LiDAR system that you see on top of the Google car over there. And the other thing that they rely on is manually annotated maps that is actually also very expensive to get, and it's very difficult to scale. Right. So one of the things that my lab is pioneering in is trying to look at how we can bring down the cost of the system such that we can actually have it in every single car. So one of the possibilities, right, is to use cameras, which are quite cheap. And what I'm going to talk today is going to be about showing you a couple of things that we need to solve in order to be able to use cameras for self-driving cars. Okay, so, and the other thing that we would like to have is having as little prior knowledge as possible, such that we don't need to rely on something that humans have to manually annotate, right? So if you think of the state of the art, how computer vision is these days, what is exciting in terms of self-driving cars is that basically we need to almost solve every single task of computer vision. So we need to be able to reconstruct the environment in order to not rely on these 3D expensive sensors like the LiDAR. We need to be able to estimate how our car moves, as well as every single car in the scene or other traffic participants. We need to be able to also recognize what the obstacles that we see in front of us are, and we need to also track them over time and predict what they're going to be doing in the future. And all this thing has to be done in three-dimensional space. It's not about these flat images that is how our retina sees the world. Right, so this is very exciting from computer vision perspective because it gives us a lot of challenges, but it's quite difficult if you want to actually make technology that works in every single case out there in city centers with many people. So this is just a slide showing a little bit of what I believe that one needs to be wants to care about if we want to build technology that can put self-driving cars in our streets. So the first thing, right, and many other speakers today touch upon this, is data, right? So Uber has a lot of data, but there is only a few companies that have a lot of data. So one of the things that we need to work on is how can we make data available to every single researcher out there to try to solve this task. Also, in academia, we focus a lot into trying to solve every single individual problem, but we should actually try to solve problems together in terms of, self-driving cars. We need to do, all these different tasks that I mentioned before. And we can handcraft what are the algorithms that these self-driving cars need. We actually need machine learning to learn representations that can solve all these different tasks, and that's actually really exciting. And we need to also take into account efficiency of our algorithms, and this requires software, clever algorithms, but also requires understanding hardware, and what is the hardware of the future that, say, in 5 years, we're going to be able to use to put in our cars. Okay, so I'm going to just touch briefly with a couple of videos in all these different aspects, just to show you where the state of the art is in terms of imaging. So one of the things that my lab did a couple of years ago was actually collect data to share with the community such that everybody can participate, can actually build algorithms for self-driving cars, and do not need to actually buy one of these platforms because they cost around $1 million, right? So hopefully, yeah, display. So here is the car that we use. This was collected actually 6 years ago. And so we collected in conjunction with the Karlsruhe Institute of Technology. So you see here the car driving around, all sorts of really complicated scenarios. And what we did with this data is actually build challenges, competitions, like the Kaggle competition, where people in both academia as well as industry will participate and try to, push forward the state of the art. It's been, 4.5 years of a lot of successes in this case. So it's been, more than 20,000 downloads of the data. There is many, many groups out there, every single group in academia, and most of the, industry labs are actually working with the data. So that was quite nice to see. Then we need to solve the different tasks, right? So let me show you what the current state of the art is for these things. So deep learning is everywhere, from every single, trying to build algorithms for every single one of these tasks I mentioned. So here's an example of reconstruction, and what we will have tried to do is try to build very accurate algorithms that actually are also very efficient. Okay, so hopefully this video plays. And you see here with 2 cameras mounted on top of the car, what kind of reconstructions you can get these days with deep learning. Okay, so you see that basically up to 40 to 60 meters, you are almost as accurate as Velodyne 64 that cost $100,000. Okay, so that's actually very good news for driving in our cities. Other things that you need to do is try to do semantics, reconstruct, not only reconstruct what is out there, but understand what's that a car, what's that a pedestrian, what is there. So again, how do we build systems these days? So what we develop is, again, deep learning algorithms that reason in three-dimensional space, because when you do driving, you not only need to know that there is a traffic participant in front of you, but you need to know exactly how far away it is from you. Okay, so I'm going to play, hopefully, a video of what this looks like. So this is basically doing 2D and 3D object detection independent per frame, and this is basically the state of the art in terms of using just a single image. So it's pretty good, right? It's actually quite accurate, despite the fact that we don't use any temporal information for these results that I show you here. Okay, so we are actually quite close to be able to just put this, on the roads, and this is real-time performance. Then we can, try to, as I mentioned before, try to put models that reason about many, many things, not just every single frame independently and just doing, for example, recognition, right? So here's an example of, in this case, we're going to have a video with a single camera mounted on top of the car, and we are interested in reconstructing everything that is going on in the scene. From the traffic situation that you see on the bottom left. So this is a bird's eye perspective of the scene. You see a video of a scene the car has never driven in, right? It's a different city. And what you see up here is the estimation of the ego car in black. The field of view is this 130 degrees that you see, as well as the estimation of where are the different cars in the scene. And also they are color-coded by their intention. What do they plan to do? Okay, so this is basically what a single camera can give you that now you can do control. Right, so once you know everything that is going on in the scene, then you can basically say, should I turn left, should I turn right? Okay. And as I said, this is trained with only a few scenes, and these are totally new videos that the system has never looked at. It doesn't use maps or anything like that. Okay, the other thing that we need to do as well is localizing where the vehicle is at every point in time. And this is important if we want to be able to drive from point A to point B, but also if we have an electric vehicle that has to recharge its battery, right? So it needs to have accurate positioning. So the way that companies typically are doing this these days, like Google, is that they record the environment of how the world looks like. They store a huge data set. And then basically when they go and drive autonomously, they look at where have I seen this scene before? And typically they drive just before they're going to drive autonomously, so that you have a clear, fresh picture of now the scene with this day, it looks like this. So this is not very scalable, right? And maybe you need to be a multi-billion company to actually do this job. So what we look at is how can we do this process but in a very cheap way without needing to record the appearance of the world. So it turns out that the motion of the car is indicative enough of where you are actually driving, because the road topology of our roads contrives where you could potentially be. Okay, so what you're going to see here is maps that are just topological, download from OpenStreetMaps. They are free. More than 50% of the world is available for you, okay, you can just download it. And then basically we estimate the trajectory of the car and we estimate where the car could be. So it's going to start with a uniform distribution of where the car could potentially be, and it's going to very, very quickly pinpoint where is this car. So in this video, what I show you here is with very small, relatively small area, and so we run this also with the area of where we could potentially be is the whole city. So it takes around 30 seconds of driving to localize with the precision of a GPS that costs $50,000 at the time. Okay, and this is again, it's free. You just mounted a camera on top of your car, you go and drive. Okay. And it's very low bandwidth, right? You don't need to actually record the environment, record how the world looks like. Unfortunately, I cannot feed forward the video, so if you are interested in seeing, when we have the full city, then I will show you later on. The other thing that, the last thing I want to show you is that I say that maybe we don't need maps, but if we are able to estimate maps very accurately with, again, very little cost, we should use these maps in order to increase robustness. Okay, so the way that typically maps are built these days, and this is, here Maps or Uber is doing exactly the same thing right now in Toronto. They have 64 cars here. What they do is that they drive around with these fancy sensors, right? And if you think about it, what's happening is that you have this myopic view of the world that is only what this car or these 64 cars look at, right? So. But if you think about it, right, there is so much information out there that we could use in order to create our maps. Satellites go around the Earth twice a day. That data is up to date and it's available for us to actually do inference. We have planes, we have UAVs, we have all sorts of things, drones that we can use. And I'm just going to show you an example of how you can use, UAVs or drones or cars, everything together in order to build HD maps automatically. And hopefully this plays. Okay, so HD maps here means that we want to estimate where the roads are, where the sidewalks are, where the parking spots are, as well as how many lanes we have. In this case, we're going to use imagery captured from a plane as well as imagery captured from a car in a subset of the data. Okay, so they don't need to overlap fully these different sensors. And what the video is going to play basically is simply the estimation that we have projected back into what the car looks like. Okay, so this runs very efficiently. It takes 3 seconds per kilometer of road, so you can actually run it even in an academic cluster for the whole world. Okay, and hopefully we'll play. Yeah, and with this, I'm just going to conclude and say that, this is more or less the state of the art in what computer vision can do these days. In conjunction with other simple sensors, I think we are very, very close to actually arrive to doing self-driving cars in cities with safety. Okay, thank you.